Hello, in this video, I want to show you a proof by contradiction where we're not trying to prove an implication. Okay, so we're going to prove the very famous result that the square root of 2 is irrational. So this is just a statement. It's not an implication, but it's a statement we can prove. Okay, so the goals, my learning objectives, are for you to understand the logic of a proof by contradiction when the statement being proved is not an implication, and to understand that the square root of 2 is irrational. And then in class, we're going to do a few more proofs from number theory, a couple of them, that building on this kind of idea where they're not implications. Okay, so what are we going to do? As usual, if we're going to do a proof by contradiction, we should signpost, tell the reader we're doing that. So, oops, I didn't want to move my R. I wanted to use my pen. So I'll tell the reader where my proof is starting, and I'll say that we'll proceed by contradiction. So what that means is that I have to assume that the statement is not true. Okay, so i.e. we'll suppose for contradiction that the square root of 2 is rational. Okay, and so now we're kind of back, at least for a little while, in that same framework of the direct proof poem. Now that we've supposed this, what we need as input to get the proof started is something we know. Okay, and the thing that we know here, and almost always in a lot of the proofs in this class, is a definition. Okay, the definition of a rational number. So we can say, thus, well, there exist integers p and q such that the square root of 2 is equal to p over q, and p and q have no common factors. So in other words, we've written this fraction in lowest terms. Okay, we've taken all the common factors out of p and q. So this is believable. So now we've written down what we wanted to show, we've used what we know, and this is computation time. Okay, so we can say, let's go to the next slide over here, the next page. So we can say, since the square root of 2 is equal to p over q, well, what are we going to do next? Well, we want to work with integers, right? And so on the one side of this equation on the left, we don't have an integer. Let's get an integer by squaring both sides. Okay, so the square root of 2 is equal to p over q. That holds if and only if 2 is equal to, actually, let's not say if and only if there. Let's say that it does imply that when I square both sides, I get p squared over q squared. Okay, and let's see. I don't like fractions either. I like to work with integers. All my theorems in number theory are really about integers. So let's clear denominators as well, and then we'll get 2q squared equals p squared. Now, what did we show in class? We have this result from class that says that if a square is even, that like if x squared is even, then x must have been even, and we can use that here. So we can say, since all this, comma, and we know that x squared even implies x even, we see that P must be even. Because P squared is even, right? P squared is equal to 2Q squared. Therefore, what can we do? Well, if P is even, then there exists an integer K such that P is equal to 2K. So we've used another definition, another thing that we know in this proof. And now we're going to start another computation. Note that, well, picking up from here then, 2Q squared equals P squared then has to be equal to 2K, the quantity 2K squared, which is 4K squared. So what do we have? We have 2Q squared equals 4K squared, and I can factor a 2 from both sides, so that implies that Q squared is equal to 2K squared, and hence that Q squared is even. So now we get to use the fact that we already used, that x squared even implies x even. If Q squared is even, therefore Q must be even. This is the contradiction, right? Because now we've proved that P must be even and Q must be even. In other words, they're both divisible by 2, so they have a common factor. But when we started this proof, what we assumed is that P and Q have no common factors. Okay, so that's the contradiction. So I'll write, but then P and Q are both divisible by 2, which contradicts our assumption that they have no common factors. So therefore, we conclude that the square root of 2 cannot be rational. And we're done.